talk about conductivity of the water. So the conductivity of water is nothing but the capability of the water to transmit electrical current. Okay, and this capacity is directly related to the amount of salts in the water, and we can also say the amount of the mineral or the salt impurities in the water is sometimes also called as TDS. So the TDS and electrical conductivity are directly related. So if you are measuring electrical conductivity, so indirectly you can measure the TDS of the water also. So normally in the salt there are lots of ions in the water, so they break up into positively and negatively charged ions, and these ions are mainly the carrier of the electrical current, or you can say the carrier of the electricity. Okay, so normally in the form of ions we have chloride, nitrate, sulfate. Okay, these are the different ions. So we have positively charged ions also and negatively charged ions also. And normally in the ultra pure water or the pure water, these are very, very poor conductor of electricity because they don't have free ions in the water. And this conductivity is also related to TDS, as we saw in the first point, and it's also affected by temperature. So the temperature is rise. So normally the rise in the temperature, okay, raises 2 to 3%. If the electrical conductivity of the water is increased by around 2 to 3% for an increase of 1 degree Celsius of the water temperature. That is why sometimes you see the temperature factor is also counted when we are going to measure the conductivity of the water, or it's called the master factor. Now you can see these are different kinds of water. So we have, first of all, you can see these are, in the first one we have salts, and these are easily dissociated or break up, and the tap water has less ions as compared to the ionic water, and distilled water has no ions. They have no ions to conduct, so that's why the distilled water has lower conductivity as compared to the tap water and the ionic water. Okay, now how to measure the conductivity? So normally we have different kind of probes available in the market. So some probes are handheld and they can be easily carried, and some probes are basically you have to be, that's coupled with a multimeter. So normally conductivity can be measured either by 2 AC bipolar method or electromagnetic induction method, and normally in the bipolar method you are going to measure the current that is being passed to the 2 pair of electrodes. Okay, and the second one you are going to measure the induction current that is generated by 2 coils. It is immersed in the solutions. Okay, so you can see here we have different kind of probes. This is a Hach probe. So normally a Hach probe, you can see this is a Hach probe, so which is made of plastic. So we have the one is the inner electrode, and this is the reference electrode. So, and this one is a multimeter. So the multimeter normally behaves also as a pH meter or a conductivity meter or DO meter, or sometimes also as a BOD meter. So it can behave as a multimeter. Okay, so you can see we have different 2 plates which is coupled with a voltmeter, and normally around voltmeter we apply alternating current, or you get AC voltage. So when they come in contact with the ionic solutions, so these ionic solutions which carry different charges, so the negative charges are attracted to the positive pole, or the positive charges are attracted to the negative pole. So there is a voltage is applied to the electrodes, and the resulting electrode is used to to find out conductance. So normally these kind of current depends on 2 factors. First of all, the conductive nature of the solution, then the amount of ions. Second, the length and the surface area and the geometry of the electrodes. Okay, so this is the way the conductivity is measured. So you saw in the preceding slides that 2 metal plates were placed in the solution. There is a potential difference applied because of the different ions in the water, and the conductivity is nothing but the reverse of resistivity in terms of physics, and it is determined from the voltage and current values according to the Ohm's law. We know what is Ohm's law. V is equal to IR. So G is nothing but I upon 1 upon R. Okay, R is resistivity, and it is also expressed in the forms of current upon E. E is the voltage and I is amperes. Okay, now as you saw, we applied an alternating voltage to the electrodes of the exact dimensions. Okay, and then the salts which were there, they dissociated and they act as a current carrier. The ions are going to act as current carriers, and the current flow is directly proportional to the total dissolved solids, any the ions in the water, and the physical dimension of the conductivity electrode are referred to as self constant. So the self constant is a new term. The self constant is nothing but the length upon area. So the distance, this is nothing but the distance between the plates, which is 1 centimeter, and the area would be 1 into 1, this is 1 centimeter square. So self concept will be 1 centimeter inverse. Okay, now what are the protocols? How are you going to measure conductivity? So we all know that drinking water and the distilled water, the deionized water, will be having lower conductivity as compared to the ionic water, or as compared to the sea water. So normally you have to, first of all, you have to make sure your water is temperature is at room temperature. You have to bring down if it is lower or higher, and also you have to make sure that your probe is not totally immersed in the water, so only part is dipped, and the conductivity is measured with electrical conductivity meter. So we know that the voltage applied between two electrodes, and this drop in voltage is caused by the resistance of the water that is used to calculate the conductivity per centimeter. Okay, so now there are several models and like the separate prototypes available for measuring conductivity meter. So some models may measure conductivity in increments of 10 microsiemens per centimeter, and some will measure in 1, and some can also measure in terms of other values. Okay, now what are the units of conductivity? Normally units of conductivity is Siemens, which was formerly called MHO, and you know that we already discussed the cell geometry also affects conductivity values. Cell geometry means the area, surface area, or the length, and the standardized measures are expressed in specific conductivity unit, that is Siemens per centimeter. And this is a product of, as we saw that it was a product of measured conductivity and electrode cell constant, and the A and the C is nothing but G into L upon A. G is the measured conductivity of the water, and L is the length, and A is the area. Area was 1 centimeter square. Okay. Now I told you earlier that TDS and conductivity are related. So normally the TDS value is 0.6 to 0.7 times of the conductivity. Okay. Now we know that this is influenced by the number of ions. Okay, so if you measure TDS, you can measure, if you measure conductivity, you can know the TDS by this relationship. Okay, now the methodology already discussed that we have to bring down the room at room temperature, and also you need to have a clean beaker. Also you need to, if your conductivity meter is dipped in a solution, or if it is dry, you need to clean, or if it dipped in a solution, you need to remove the cap, and also you need to wash them with a clean tissue, and you need to gently dry them, and also you make sure that you don't rub or stroke the electrode while drying, as it may damage the probe. So this is the conductivity of various kind of solutions. So pure water has lower conductivity, demineralized water, distilled water, tap water. So these are the values. You can see the seawater has a very, very high conductivity. Okay, and the 5% sodium chloride also has a very high conductivity and 10% sulfuric acid solutions also has a very high conductivity as compared to the pure water and distilled water. So now how to store the probes? So after measurement of the conductivity using a probe, you need to store the conductivity probe immersed in DI water for a few minutes, and you can also store them dry. It depends on the type of probe you're using. Okay, so before drying you should soak them in DI water so that to remove the filth or impurities, and also you make sure that there is complete wetting of the electrodes if you are capping them up with the aqueous any electrolyte. It will depend on the type of probe you're using. So thank you.